Well met, 216ers. This is Professor Kaufman, and what follows is a video overview of 216's Project 2 for spring 2025. You'll find the project links off the course schedule. That's Prof K 216 schedule.html. Scroll down just a little ways and find where the deadline is listed. It's next week, Friday. And click on the link to take you to the Project 2 specification. A few notes to get started. You can see the outline over on the left-hand side involves three problems. And contrary to the previous project, this project has three distinct problems that don't interrelate to each other. So you can take them in any order. I don't have any particular recommendation. I think going in linear order of problem one, problem two, problem three is fine. Just be advised that each of them is of modest girth. And so you'll want to start early in order to allow enough time to complete all of them in a stress-free setting at any rate. And there have been a number of students who reported it's difficult because they run out of time. And taking it linearly leaves, in some cases, if you start too late, not much time to do the third problem, which is similar to what we've done in a lab previously, however, of somewhat more complexity, and you don't want to submit late to this. So you've been warned then about the challenging part of this. It doesn't all tie together, so you have to sort of reset throughout a couple times throughout it as you work on the separate problems. During this overview, we'll take each of those problems in turn, going in linear order, and give you a few details to get you oriented on that. As was the case before and is the case for all the labs, there's a code pack associated with the project. We'll download that and do a little bit of setup shortly for it. And generally, the problems address three separate domains. The first is something we got through in lecture the other day, and we'll not have a chance to practice bit level manipulations. So operations that modify values at the bit level. And we'll see an actual application for that, which is somewhat reminiscent of how it's used in the real world in some settings. The second problem deals with use of the debugger, and GDB will be used to address this Puzzlebox program that requires certain inputs in order to earn points. And finally, we'll do a little bit of basic data structure programming to code up a hash set in the third problem. The code manifest is here, and this includes all the things that will be downloaded, along with some things that you need to create. Each of the problems has something that you should create or at least edit associated with it. So out of the gate, in most cases, the test cases won't run. You'll actually have to create some files to get compatibility with the provided make. But that thing reads more or less as the project one did. I type make help to get the different targets or remind you how to run an individual test. If there are bugs detected in the project that require an update, then a make update will work. And then a little diatribe here about things you probably already know. All right, down to the problems. The first problem, it deals with bit level manipulations, and this is set in a setting where you have an actual physical device that you're trying to code. And this is one of the most common tasks that's done using something like C. It's low-level embedded programming, embedded in a device of some sort. Now, it's a bit of a misnomer because if you're looking at this on a laptop or a desktop, that's a sort of embedded thing. But what's usually meant is a little microcontroller, sort of small CPU that's in a device. It's a cheap CPU, so it doesn't have a lot of power to it, not a lot of memory, but it doesn't need to do a lot. And so the case that we'll study is a digital scale. If you've not ever had experience with these old tabletop scales, they're super cheap. You can get one for like 10 or 15 bucks off of Amazon. And they work sort of as advertised. You put something on it and it weighs how much it is. So for instance, this bowl right here that's on the scale weighs 7.1 ounces. To make our lives a little bit easier, we'll deal only with the so-called imperial units. So the scale that we'll code is only dealing with ounces and pounds, sort of standard American units that are used almost nowhere else in the world. But they have the nice feature that there are 16 ounces in the pounds, which will give an opportunity to do a little bit of conversion, this being a power of two out there, without actually having to divide stuff. So you can select between those two units of display. And the scale is able to sense things at increments of 0.1 ounces. You can see that with a little decimal place over here. There are a few other sort of features to it, but the one that I want to spend just a moment on because it may be unfamiliar to you is the tear feature. It was something I wasn't really familiar with when I first saw scales like this, but it's super handy. Basically, it allows you to weigh some contents of a container. And so the bowl that is here is not what we want to weigh. We want to weigh how much oats we're going to go into the oatmeal, something like that. And so most scales that are like this, they'll have a tear button, which is Arabic for that which must be removed. I know there's some history there. You can sort of look it up. So on putting some object on it, you can press the tear button and this will zero the scale. If you were to take the bowl off, it would read negative now because it's stored internally the weight that was previously on there and is subtracting that from the current weight. With the bowl still on it, it's the current weight 7 ounces minus the stored weight 7.1 ounces. But if you put then in something additional, then you see only the weight for the additional thing in there. And so this tear feature is something that will code into the scale. It's not terribly hard, but requires some hardware that the scale actually has to have a little memory unit that remembers, like, this is the last weight was there, and the tear button stores that. So at any rate, if that's a little unfamiliar, you could click around, watch some YouTube videos about it. It's not hard to get to. But this tear term will be referred to because there's a button to push for it, but also then a stored tear value that allows for it. Aside from that, the only other features that you need to be aware of is the ranges. You can go from 0 to 99.9 ounces, and that's just on account of there's a limited number of digits on the display that we'll have. We'll see that later in a second. Yeah, if the internal sensor is out of that range, either negative or above 99.9 ounces, then there's an error that's occurred. Okay, so the features of the hardware exposed to C programs when you're embedded, doing embedded programming, oftentimes through global entities like global variables. And so some of the features of the scale here show up as global variables in C programs. You won't need to define these. Instead, they'll be defined in the little simulator code that's provided, this scalesim.c, and are declared in the header file as extern, as in this doesn't declare the variable, it just states that it exists and may be used by other parts of the program. So the sensor, the thing that's actually reading weights over here, is exposed as scale sensor port. This port being sort of hardware connections to some part of the hardware that read as a variable sometimes. It's a short 16-bit quantity and is signed, so you can see positive or negative values from there. And it's, again, in increments of tenths of an ounce. So if it reads 238, that's 23.8 ounces that have been placed on the scale. Generally, this is a sensor, so you should only read from it, but it's a C, so you can do other things. In an actual hardware setting, if you try to write to it, it'll probably trigger some fault or something like that. There's a second hardware feature that stored tear value. So this is where you can place a value that was previously stored. Again, so going back to our bowl example, you press the tear button here, and then this variable is set to the 7.1 ounces that the bowl weighs. And generally, then the weight would display whatever the current sensor value is minus this value. If it's 0, then nothing shows up there. A status port, which indicates certain features of the scale. And this is an unsigned character, 8 bits. However, the bits don't constitute a number. They instead constitute a series of flags or on-offs. So there's at bit 2 a unit select, so that if it's 0, then you should display in ounces. But if it's instead of 1 there, someone has pushed the little unit button over here and changed it over to pounds. So this quantity should be divided by 16 so that the poundage is shown instead. And then there's at bit 5 an indicator of whether or not the tear button is being pressed at this moment. And in that case, there'll be a special behavior to, instead of showing the weight, take the current weight and store it into this global variable, the tear value there. And finally, there's an external part of the machine, the display, which is this little LCD panel over here. And that's controlled through a C variable that corresponds individual bits to parts of the display. So we'll see in a second that this little bottom part of the 1 right here, there's a bit that controls whether that is on or off. And a certain bit pattern then shall cause a 1 or a 2 or a 5 to show up in this. And similarly, a series of 1s and 0s would cause the 7 to display here. And the little ounce indicator for the units up there, that's also controlled by a bit, so it can be turned on and off. And those bits are spread across this scale display port. It is described in some detail later on, and we'll go through some parts of that. So if you're getting a sense that, like, okay, there's context to this particular problem, it's not just a code this data structure, that's good. And this is fairly common for lots of applications, particularly embedded ones. You have to get acquainted with the machine and what the individual bits in the C program will do to control physical parts of the machine and interact with that. That's an oft-used case for C. Now, in the process of doing this, we'll break the series of like setting up the display after reading what the scale sensor value is and subtracting off the tare and so forth into several steps. So there'll be a little bit of information communication between that. And so there is a series of things in the header file that defines useful encodings of information. There'll be this scale T struct that encodes what weight to display, what mode the scale is in, whether it's supposed to show the weights, store the tare value, or some kind of error has happened. So sets this mode to be one of these things. And then a character that is, again, 8 bits that are indicator lights, as in not weight to show, but turn on or off the ounce indicator, turn on or off the pound indicator, turn on or off the tare indicator. And there'll be a little button up here. Yeah, I think it's even here. It's like there's a tare sort of indicator up here to indicate someone has previously pressed the tare, so the tare value is non-zero in there. And so, this display is set up. It's nice to have the weight separated from here's some additional indicator lights. And so the actual code that's run will be periodically running a function called scale update that you'll write. But since it's a semi-complex task, we want to be able to debug it. It's broken into 3 steps. So here is the outline that we'll copy in a minute to start running test cases associated with problem 1. There are 4 functions: a scale from ports, scale display special, scale display weights, and scale update down here. And I'll just talk through each of those quickly. The objective of the first function is to read those global variables, the ones that are listed up here, and construct one of these little guys over here, the scale T. That involves a number of special cases. For instance, if the weights were out of range, like it read 2,000 ounces, then you should put the scale into error mode by setting this scale T here, setting its mode to the mode error up there. If instead it read a normal weight, like 83.9 ounces, and someone had previously pressed the tare, so something subtracted off, then you subtract that off, set the weight to be whatever 83.9 minus, it was 10 ounce container or something like that, so 73.9. And also then set indicators to say, oh, I'll turn this bit on to say I'm in ounces mode, and turn this bit on to say that the global variable, the tare value, was non-zero. So I'm subtracting off stuff, and the user deserves to know that. On constructing that little thing, it's used in the second set of functions, the scale display special and scale display weights, to construct a display. And generally, scale updates just calls those 2 functions along with a few other things that get the job done. So we'll spend the rest of this talking about the scale display weight and scale display special functions, which take in as an argument this scale and then manipulate the bits that are pointed to by this display integer to construct a display, so it shows meaningful information. This is a bit involved, so let me come down to some diagrams here that you'll want to refer back to often. Here's a complete example of one possible display where 83.9 ounces are measured on that scale. There are 4 LCD digits over here, and each of the little panels over here, this one's not darkened, this one is darkened, is controlled by one of the bits. And they're subdivided up here where the bits 0 to 6 here, they control this first LCD panels over here, so that if you plop down this bit pattern where only the fourth bit here is a 0 and everything goes on, then it looks like a 9 over there. And then the same setup over here, starting from the top, 7, 8, 9, 10, 0, 1, 2, 3 across. This is what controls the next digit over with this particular bit pattern where the 8 and the 11th bits are missing. And that shows something that looks sort of like a 3. Little decimal place here is always on because there's always display of, the sort of tenths of the digits over here. If all of those are blank or zeros rather, then you end up with a blank over here. And then certain other bit patterns can show things like 8s or negative signs, or in the case of an error condition, something that sort of affects something like an error. So ERR for error over here. Finally, then, over at the high end of the bits, so this 27th sort of comes over here to the 20th, 29th, and 30th bits. They control some of the indicator lights, where in this case, someone wants it displayed in pounds. And so this 29th bit is set so that the pound indicator is on. 28th bit is 0, so this ounce indicator is off. And there is a tare value. And so that non-zero thing is indicated with a little tare being on here, 30th. And so that's the source of where these indicators in the scale come in. There's three possible indicators aside from the weight to display. And the job of the second two functions, this scale display special and scale display weight, is to construct a display that looks like this. With the scale display special limited to two cases, either showing the error here or showing special store as someone is pressing the tare button that the value is being stored internally. The more complex situation is the weight one, where you have to fish out, like, okay, the weight says I'm supposed to show 83.9, so I have to arrange this series of 32 bits that are listed up here to get this thing up on the display. Now that's made easier somewhat by the pattern that's here, where each of these digits can be individually set, but the pattern is the same for each of them, that the rightmost bit in each of these controls the top panel here. The next bit over controls this sort of left thing here, so you can see there's a 1 for the 9, but a 0 here in the 8th bit, that's the second bit over here. And so a good strategy to make this, to facilitate this, is to figure out what are the bit patterns for each of the digits. A handy diagram down here allows you some ease of access. And a lot of you will just take this thing and code it up to establish an array that has in the 0th element this bit pattern, so that if you determine, oh, I need to display a 0, then you can go fish out the 0th element of the array and get the bit pattern to show a 0. And likewise for a 1 and a 2 and 3. And there might be a few other things that you'd want to plop down, not necessarily in that array, but define it someplace. For instance, an E or a negative sign or a blank. There's some overlap in that the 7 and the T are supposed to be about the same, and the S and the 5, the 0 and the letter O are the same. As you would want to show something like store, it would actually be 5, 7, 0, and then the A or R by that letter down here. So there's some advice about how this looks, along with how to go about using those digit patterns, along with the bitwise operations that we have established to create a starting blank display, perhaps all blanks like this, and then plop down at some position, for instance, this position 0 to 6, a bit pattern for 9, then create a bit pattern for 3 and shift that over and combine it, probably with an OR on this, and then create a bit pattern for 8, shift that over further to the starting at the 14th bits, and OR that on to combine it over here. So that's the general process that one would go through in order to create a complex display of this. Each piece follows the same pattern, so create those pieces, align them, and then add them. And the notion of adding in this case is usually going to be a bitwise OR operation. The only thing remaining then is to plop down some special cases. The indicators over here, possibly a negative sign. And you can see that there are a few sort of special cases that you don't have any leading zeros if there's only one digit over here. This thing, if it's single digits, then it will always be a 0. So make sure to account for those things, and the test cases check for that stuff. So if you're off a little bit, then you'll see some failures on it. There's myriad examples that show up lower down here that are in a provided file, this scale examples. And you can see down here that there's a simulator, a main that you don't have to write, that once you've completed your scale updates and have the right code in there, you can run this thing and it will output stuff over here to say this is what the display looks like for these sensor values, the sensor value, the tare value, what the weight mode is, and whether or not the tare button is being pressed at this moment or not. So tare no, tare yes. And so it's worthwhile to study some of these examples. Some of them are reflected up there, but you can see here the actual bit pattern in the display port is laid out. And this rightmost bit here is a 0. And that means the top panel of this 4 is missing. The next one over controlled this part. So there's a bar here, and the one after there's a bar here, and there's another one here, which is this middle panel for the 4. And then as you go further over, there's 2 zeros. So that's this bottom gap right here. And then the gap down here, that's the bottom part that's not shown for a 4. And then it ends here with this 7th bit for the right part of this 4 over there. And then that same pattern of bits is used here, grouped together for the 1. It's just that there's a different series of ons and offs in this case in order to show the 1 and the 7 up there. Some special cases are also shown down here for, so if the tare button is pressed, then you're supposed to display store over there. and that's irrespective of what's over there. And well, one of the important things is like, oh, the tare value was 125, but the current sensor value is 139. So after your code runs, this value gets stored into the tare value, which is here now. They match, whereas they were different before. So I encourage you to have a look at these to get some of the special cases, some of the general flow of it. We'll now proceed to just download the code pack and set up things so that you can run the tests like out of the gate on that. So go back up to the top of the spec here. I'm going to copy this link address and then zip over here to my terminal. My list, I've only got P1 code stuff here and some old stuff. Let me actually take and get rid of this old stuff that I don't need anymore. So let's here. I'll do a wget on that web address for this thing, which will, if I refresh, I got my P2 code now. And we'll unzip the P2 code zip and then change into that directory. I'm going to get rid of this zip now because I don't want to inadvertently submit an empty zip for my completed project. As you'll see over here, there's the scale main, the scale sim, the header file that has the stuff, some of the stuff that we discussed in it for reference. There's also additional stuff here that has to do with the simulator. And you don't necessarily need to talk the sort of understanding of this lower down stuff. But if you're curious about how the simulator, the software simulator for this hardware device works, then you're more than welcome to. But if I type a make prob1 in order to try and build that, oh, sorry, I need to change into P2 code here. Prob1, you'll get an error because there's a required file scale update.c that you'll need to create. And the outline for that is given in the spec. So let me here just create a scale update.c as indicated in the manifest. This is something that you have to make. It's where you'll write most of your code. Then I'll come down here to the scale update outline and do usual bits to copy and paste this stuff. Not quite as long as the previous project and so forth. Okay, so this is now present. We need dummy bodies for each of these. And so I will just return 0 in this case. Return 0 here. And then down here for this thing, return 0 as well. Okay, with that, this is now a valid C implementation file. And if I buzz back over to my shell and take make prob1, let's see. Something's a little bit wrong here. Let me pause for a second to diagnose this so I don't look too dumb. All right, sorry, I neglected. I wrote 3 function bodies, but I'm still missing the display weight one. I missed one. So if I come back over to the scale update here, I just missed this middle one here. And return 0 there. Okay, so I'll come back to the shell and do a make prob1, and we're good to go there. I can also now do a make test prob1, and this will run the 40 tests associated with this thing. There's quite a few, in part because, well, may as well start saying this now. This is not the last time that we will deal with this scale application. Rather, we'll work on this thing a second time in Project 3, where we'll recode these functions in assembly. And if you find yourself thinking, oh, this is pretty easy to code in C, that's great. Just make sure that you write as concise and a clean code as possible, because these are things that you will then translate down into assembly. And so some of the constraints that are present here are relative to that. Limit the complexity as much as possible to these functions, because if you have a nice, clean, short roadmap in C, it'll be much easier on your future self to translate that down to assembly. There are a few other constraints there are mentioned here. For instance, the display functions aren't supposed to mess around with global variables. You're not to use any floating point operations because the microcontroller that's involved doesn't have any floating point capabilities. So you have to use all integer operations and avoid using certain math functions. So no floating point unit there. So be mindful of those constraints there so that, again, you have an easy time translating to assembly later on. You don't lose any style credit because Test cases can pick up on certain things, but they won't be able to pick on whether you're temporarily using floats or something like that. That'd come around to haunt you in the style criteria of the manual inspection. All right, problem 1, I think more or less sort of covered. Let us move on to problem 2. Now, this one is entirely different in nature. You're not going to code for this, rather you're going to debug. And there's a program that's provided in the code pack called Puzzlebox. Let us just buzz over here to the shell and see how that thing looks. You make Puzzlebox here. I think it's make problem 2. It's here, and you can run it with Puzzlebox there, and you can see it requires an input file. For your convenience, there is in here a provided input.txt, and the first thing up here is something you'll fill in with your directory ID in a second. If we provide that, it'll complain a little bit, input.txt. And your directory ID is not a valid directory ID. It has max 8 characters. This is supposed to be the first part of your UMD directory ID. So I'm going to plop down CCOFMA2 because that was in a previous lifetime my directory ID. I think that's about right. Cool. And now if I run it with this input.txt, then I'll get still something that's a little bit less than stellar. So here's a 0 out of 30 possible points here. Now, if this is all there was to it, then it'd be sort of a lame exercise because it's a guess and check at this point. However, there is some more information you get because the source code for Puzzlebox is present here. Let's have a quick look at it. Change that, find puzzlebox.c. The way that this thing is structured is that there's a main, and after doing a few preliminary checks, all it really does is to call a series of phase functions that if these things return, then more points are added onto your score. There are 10 total phases, and we'll talk in a second about how many you have to complete for full credit on that. The phase functions themselves appear a little bit lower down after some stuff here. And you can examine other stuff you want. It's only of mild utility. Let me find phase 1 because that's where we're at right now. Here it is. So there are 3 numbers that are read, and this next input function is going to read them out of the file, that input.txt. And then there is a modification made to the A that's over here. And then a certain condition is checked, the A versus the B versus the C, etc. here. And in order to make it through this phase, to return from it, you have to make sure that A, B, and C satisfy this. Now, if you recall from just a second ago, I'll pull up that input.txt. I selected the A and the B and the C over here. They're the things that are read in, so I have control of this. What I don't have as much control over is this hash value, which is a quasi-random value that is computed based on your directory ID. And since all of you are supposed to have different directory IDs, and during manual inspection we'll check, did you put your own directory ID in there, you'll each have somewhat different values for this hash, which leads to different values that you'll need to satisfy this set of constraints. The only thing that changes is A over here, but because there's no printing in here, I don't know exactly what does A become after adding on this hash value. You very much could, just insert some printfs here to try to get this and recompile and run it. But that's not the point of the exercise. And so if you're looking to circumvent this in some way, just take this as like, okay, yes, I could take the elevator up, but if the point is to get healthy, I should take the stairs and do my stairs out there. Then make use of the debugger to solve this. It'll be good training and also excellent preparation for project 3, where you'll have a similar setting in assembly and adding printfs will not be an option. So in order to do that, I'm going to bop over here to the terminal and fire up a proper terminal because I want to use the text user interface for GDB. My go-to normal terminal is GNOME terminal, so I'll fire that up. For some reason, it always launches in the background here. Increase my font size a little bit. Do a listing, you see we're here. So to run GDB on Puzzlebox, you'd cant the following chant, GDB. If you want the text user interface, the TUI, this -TUI, and then the program, Puzzlebox here. This will change the screen, and let's see. Oh, I spelled it wrong. Let's see, Puzzlebox. There we go. Cool. All right. So this gets me set up here where I can see there's the main function and so forth. And I'm interested in debugging this particular function, this phase 1. So I'll set a breakpoint, break at phase 01, and then do a run here. And you can see that here there is, let's see, exiting, no process, run starting program related to Word. Okay, hang on a second. I paused to make sure my GDB is configured right here. Yeah, one of the problems with this TUI mode is like output gets intermingled with the sort of this screen display here. And we'll talk a little bit more about it in a second. For a moment, let me disable this. So TUI disable will put you in the normal command mode here. And at this stage, I've set my breakpoint here at phase 1. If I just type run, then I'll get this usage message because I forgot to set the arguments over here. I need to say, when this program is run, feed in the input.txt. That's what should appear on the command line. So that's done via a set args inputs.txt. And I'm going to put myself back in TUI mode, so TUI enable, because I like seeing this stuff. And now if I run, I should get some screen tearing here because there's some output that's been printed and so forth. And to eliminate that screen tearing, use the keystroke Control L on your platform of choice. This will redraw the screen in this text user interface so you can see something saying. And you'll see here that we've hit this first breakpoint. There's a B here next to line 272. That's in the source code. And this is where execution is stopped. Now at this stage, I'm going to make this debugger full screen. My objective is to figure out how does A change here. Right now, I don't have any values for A, B, and C. I think I might be able to print them out. And you'll see here that just as we talked about in class, they have been allocated in the stack or someplace. So they have values, but they're random values and are meant to be overwritten by the input that's coming in from the text file. So if I type a next command, which will move to the next source line here, and then print out, print A, there's lots of shortcuts in it. The one that I had in my text file, that is present now. It's been stored in A. If I type next a few more times, and handy trick, if you type next and then just press enter, it'll go for another next. Then you can see print A, print B, print C. You can also type, was it info locals, I think, and this will tell you all the local variables that are in the current stack frame here. As we're set up, this is what's been read in here. I can also print out what this hash value is, which is global, so it's shared amongst all of the functions in here. P hash, and this is a very large value. I don't know what this is, modulo 41. I could certainly compute it, but why would I bother? Would I just type next and see, okay, when A is modified, what is it now? It's 32 now. And so with my current A value of 1, adding my hash modulo 41, it becomes 32. And what I really probably want to do now is to change B and C so that I have values that adhere to these constraints and get me sort of out of this thing and net me some points. So I need B to be bigger than A. I'm going to move this to the side here, bring this thing over here, and start monkeying with this stuff. We keep A as 1. B needs to be bigger, and so maybe I'll make it 40 to start out there. And then B also has to be bigger than C, so it is right now. And A needs to be smaller than C, so C needs to be bigger than A is. But A isn't 1, it's 32, so I left myself a little room. Let's make this thing 38 instead. I'm going to save that. Right now, the text file has different information, but the program is already in flight. It's read that stuff in, and it's stored in memory. So in order to get this to work right with the new values, you need to rerun the program. That is the run command in GDB. It'll ask, are you sure you want to stop your current execution and restart from the beginning? And my answer to that is, well, certainly I am. So I'll type yes here, punch enter. Get screen tearing because some output has been printed as this thing starts to run. I'll press Control N to redraw, and we're back at this breakpoint. Now, I don't really feel like typing next a bunch of times, so I'm going to set a new breakpoint here. I want it at line 277 to stop right before this if case here. So I'll set a break there. And you can see the new baby breakpoints that's been set up because I'm not at it right now. And if I just continue at this point, shorthand is just C for that. You can learn a lot of like shorthands in GDB. This will jump over the steps here and say you've hit this breakpoint, you now hit this breakpoint too. And maybe I'll have a look at my info locals here to see how things have been set up. There's A, it's 32. B is 40, so that's less than there. B is greater than 38, and A is 32. It's less than C, 38 there. So I think we're in business. If I next here, I'm going to hit the return. And I'll next again. And this gets me to the end of the function. And if I punch one more time, then I'm up and out of phase one and into the sort of earning of points here. So at this stage, if I just continue, then you'll see I have 3 points out of 30 in the bag. And it'd be time to move on to phase two out there. I'll need to figure out exactly what is involved in phase two. So it makes sense to delete my current breakpoints, which had to do with the phase one stuff, and then set a breakpoint at phase 02. And so there are a couple ways to set breakpoints. Actually, there's a whole bunch of ways to set breakpoints. One of them is based on function names. Another is based, as we saw, on line numbers. And so at this stage, if I run and then press Control L to refresh the screen, I'll have bypassed phase one because I've got my 3 points for that. And now I want to start looking at phase two. A couple notes, the up and down arrows control this top window that allows you to sort of scroll around in the source code, but it's not a bad idea to keep a copy in full up over someplace else. And that overrides the usual up and down to recall history in the command prompt out here. But if you press Control P, rather than printing, this goes to a previous command. And Control N goes to next command. So that could be a handy one as you want to scroll through the command history over here. If you disable the TUI, and unfortunately they have two different command histories, one for the TUI and not. So if I do a TUI disable here, then the up and down arrows actually recall the same things out there. And so that can be a possible other way to get things. But I much rather stay in the sort of TUI mode and just remember Control P to go to previous commands. For those who are interested, that's an Emacs binding, and so is commonly used in a lot of these GNU applications. Sorry, Vimmers. At any rate, the general flow then that I've just demonstrated is what you should engage in for the remainder of solving Puzzlebox phases. The first one is really easy, and the next ones start to get a little bit harder. This one isn't too bad because you can see immediately, oh, it's using A to I to convert some input string into a number, so I need 3 more numbers. Generally, you want to figure out how many inputs, what kind of inputs. Are they numbers? Are they letters? Are they strings? Are they floating point things? You can sort of browse through the phases as you want, but that's the first thing is what exactly am I looking for in the input file in order to make progress on this. And then seek to see what can I control. That's in this case, there's something happening again to A, but then that's used in a different fashion to say like, oh, through this transformation over here, it's supposed to get C that's equal to whatever V is, and V appears to be based on A and B and involves the hash again. And so this is going to take a little bit more thinking, but is well within reach for all of you. So proceed forwards on that. And the further you get, the more points you will earn. If you jump over here to the spec, you'll see that there is a mention of there aren't any test cases for this, but you can earn up to 40 points for completing all phases of the Puzzlebox. If you want, I think that the scoring values, they're up near the top here of this. Phase 1, phase 2, phase 3, etc. And so if you get through phase 8 and skip 9 and 10, you've got your 30 out of 30. These two are progressively harder, but allow you to earn some makeup credits. And so if you lost credit in project 1 or anticipate you might lose a little bit of credit in project 2, then this would be a way to get some more points in your overall project pool to patch that gap. It doesn't count as bonus credits, so at the end of the semester, there'll be 500 points total for projects, and if you have 560 points, so we just truncate that to 500. But if you made mistakes earlier, lost some style points or something like that, then here's a way to make up some ground. And there'll be opportunities like this in further projects as we go ahead to earn a little bit of makeup there. But here's your first opportunity to earn up to 10 by completing all phases here. Okay, I think that's all I need to say about problem 2, which is debugging the puzzle box. The last problem involves implementing a data structure. And if you've not studied this stuff, I see I got to update this. This is from my old University of Minnesota days where it was 1913 and 1933. Those were the programming 2 at those institutions. Rather, it's 131 and 132 by you folks. You're supposed to have seen hash tables at some point. That's something that's studied in all sort of intro programming sequences, particularly for programming 2. And so, if you're a little shaky on the whole hash table thing, there's some resources here to remind you of the nature of hash table, and particularly the separate chained hash table, which resolves conflicts in the hash table where you have a collision of two things want to be at the same spot, but just saying what's at that spot is a list. And as an item wants to be added at that spot in the hash table, it goes into the list. If you study these things in Java or Python, then you should be in good shape for this. So we're going to code this in C. And it's going to have a flavor that's very similar to the list application from Lab 2, where there's a main application that's interactive. And as you start it, it prints out, here's the things that you can do. You can print what's currently in your hash sets. You can show the structure of it. You can add things to it. And you'll see then that these things show up in the hash table here. You can actually look at the structure and say, the hash code for Rick is this 2518, and the hash code for Morty, this right here. Apparently, if you take this mod the size of the table 5, you get 3, which makes sense. The last digit is 3, and so it should be at the third entry here. And that's if you take this thing, which the last digit is 9, and mod it the size of the hash table 5, then it can be 4, and that makes sense. Like 9 mod 4 is, or 9 mod 5 is 4. One interesting aspect of this is that the hash table will track the order that you add things in. And so the normal printing is the first thing that was entered in the hash table, that's the first thing that's printed, followed by things that have been added later. And so we'll see in a second, the data structure accounts for this by not only having the hashy part of this and some lists associated with the hash table entries, but also an interleaved linked list that allows Rick to point to Morty. So this is the first node, and there's an order first here that goes to Rick, and Morty's added next. So that if you add subsequent things, that goes after Morty, after Summer, after Jerry, after Beth, and so forth. And so you can print out here that this is the exact order that things were added in the hash table, because it slightly more interesting flavor to it. Down here, the actual structure of the hash table, you can see Tiny Rick is like earliest in the hash table at entry 1, but that's entirely dictated by the hash code for this string, and is the last element, but appears sort of first in the hash table entry here. You also see from the structure that over here, this entry 3 has 2 nodes in it. There's a list that has Summer at the front, followed by Rick after it. Summer was added later because Rick was here at the front of the hash table part. But to make it order 1 to add in, it's compute the hash table and then add this thing at the front of the linked list that's here, a little singly linked list. So that'll be important things to sort of account for, and we'll talk through a few more details as we look at a data structure diagram of how this thing plays out in just a second. But if this is feeling sort of like, oh, it's like the list application, that's great, because it'll be divided into 2 parts. There is a hash set main that you'll have to write, and also a hash set funcs, just as there was a list main and a list funcs. And one of the pieces of advice that we'll do in order to set up for this is to go back to Lab 2, grab the provided code for that, and then adapt it for this purpose. All right, just to continue the brief foray here, you can ask, are certain things contained in the hash table? So is Jerry in there? But you can see, yeah, but I added earlier, so this will print out found. If you look for Unity, it's not present. If you look for President, it's not present right now. And adding things to a hash table that already contains them then leads to no redundancy. The definition of the set is unique values that are stored there. So Jerry's already in it, so attempting to add it gives a message about elements not present, so nothing has changed. The last bits are to actually save and restore the hash table. So you can add some things in there, and then load up a new hash table from files that are stored. So this will involve a little bit of file I/O to take the hash table, serialize it into some text file, and then be able to reload it over there. And also then be able to restore sort of saved copies of it. There are functions associated with it that allow folks to read on their own. Finally, it would be a hash table if it stayed fixed in size. As the number of elements in a hash table sort of grows, the efficiency of adding and finding things starts to be limited. And so in most cases, you would expand it. This happens automatically for a lot of versions of hash tables. However, we'll explicitly code this. So that's on saying, I think I want better efficiency. I'm going to expand the hash table. And this will have a specific set of semantics that will double the hash table size, but then go up to the next prime number, as there's some mathematical advantages of having a prime number sized table out there. So in this case, we had a table size of 5. If you double that, you get 10, but the next highest prime number to this is 11. And this involves then rehashing everything to say, before Tiny Rick was at position 1, he happens to go, now in the new sized hash table, you take the hash code and mod it 11, and he's at entry 6 over here. Beth was at position 2 and is now at position 1 because her hash code, this 2006967, it's a different number when you mod it 5 versus mod it 11 out there. And so this is, part of dealing with hash tables is like when you want to expand, there's a somewhat complex and costly operation to expand and rehash, replace everything in here so it can be found in the new table. And lucky all of you, you'll get to code that part. Okay, I don't think there's a lot else to say. I want to take a second to talk through the visual representation of this data structure. It's kind of represented over here in this textual version of it, but having pretty pictures is always something that makes students happy for that. So the hash table is divided into 3-ish parts. There's some lists involved. So there's an HS node here. There's also an overarching HS or hash set struct that's mentioned over here. And it has several pointers to spots, certainly how many things are in it and what the table size is here. But probably the most prominent part is it's got a table. So there's an array down here. Each of these elements is a pointer potentially to an HS node. And the objective of these is to point at a list that's, these are all the things that hash to this position, index 3 here. Some are hashes there. You can see that from the last element or the last digit of the hash code. Rick hashes there. Likewise, Beth, mod 5, the table size here, the last digit is 7 there, so that would be at the second entry here. There's nothing that hashes to this 0th entry right now, so there's a null there. And the convention is usually a slash there to abbreviate that null. You also notice these blue arrows here. So as you would want to print out the entries of the hash table in order, you'd follow this order first bit. Oh, and I see I need to change this name. It was hash node, it should be HS node here. So this will point down here to the first thing that was entered, Rick. And in addition to the pointers to the next thing in this table row, there's also these blue pointers that say the order next. So table next and order next as it is. So following these blue links allows you to recreate, apparently the things were added in order of Rick, and then Morty, and then Summer, and then Jerry, and then Beth, and then Tiny Rick up here. And this is the last thing that was added in. So if we add something else like President, then Tiny Rick's order next would point at President, wherever it is in this table here. There are 2 kinds of lists that are interleaved or overlaid in here. The first kind is attached to the table entries. You can think of it sort of as rows. And then there's one sort of master overall ordering list here. And so it's your joy to code this. The structs associated with this that are in the header file, they lay this out in that there's some data associated with each node, and then these 2 different types of lists. The next thing that's in the table, and as well the next thing that is according to the order of adding in the hash table. And then this table thing sort of refers to nodes, but also allows traversal in a linear order for this stuff. So the general sort of setup for this is that will provide a hash code for you for compatibility. It's a polynomial hash code, so it has some advantages and disadvantages. It's very similar to the one that Java's string class uses and is based on that primarily. If you're interested in hash codes, you can have a look at that. Otherwise, just make use of it to say, here is something that I want to convert into a numeric representation that's non-unique, so call hash code on it. And then the primary work here is going to be in implementing the required functions that are part of this outline of the Hashset_funcs.c. There's a long list of these. They're the sort of minimal that are required. So in a second, we'll copy this over and paste it into a Hashset_funcs sort of .c file and start filling in dummy definitions so we can run test cases. And you're also then required to implement a Hashset main application. It has a few features associated with it. Some help messages here that's provided and sort of printing, along with the command set of like hash coding and contains and add and print and structure and so forth like that. Save and load, interesting stuff there. But we'll model this one very much after the thing that's in Lab 2, that list main application, because it's supposed to have some echoing features to be supported with the tests. And a good way to get the basic structure for that is just to copy something that's similar, but the list version. Okay, with that all that in mind, let's make a little bit of progress on this. We've already downloaded the code pack, so let me start to copy this outline for the functions that are required. Because if you recall up here, these two files, Hashset_funcs and Hashset_main, they are not part of the code pack. They're things that you have to create. And so if I were to come back over here, get my shell back and type make prob3, then it'd say, hey, I need this thing in order to build the application and run tests and so forth. So let's do it to it. So let's create a Hashset_funcs.c. Paste that in here. You can see the hashset.h is included in that. That'll bring in STIO and various other things that are needed there, so not for convenience. And again, the hash code function is pasted or is already present there. I'm going to take a minute to go through and fill in dummy bodies for each of these functions because right now it doesn't do anything, but I want to be able to, this is just a stub for a function, not an actual body. So I need a body in order to be able to compile and run this thing with the test cases. So over here, let's see, and this is an int, so return 0. Let me just make a copy of that because there's probably going to be a bunch of those. Let's see, is a void. Void function, void function. May as well make these things stylistically sane. Okay, so that's, I think, all of them here. Yeah, looks about right. Okay, cool. And then I could, so let's do a Hashset main pipe.c. Now for this, I'm gonna go find my find my lab 2 work. I don't think I have that downloaded right now in this directory. Yeah, so let me go grab it. Come back over here and make a duplicate of this tab. And I'm going to go back to good old lab 2, which is where we had this list main application. So as a linked list application, I'm going to grab the code pack for that. Probably you have it sitting around someplace. I've got it. I just don't want you to show you my solution to it just yet. I'm going to change up a directory because I don't want to do this in the P2 code stuff. And wget this here. There, so that'll make the lab 2 code, and I'll unzip that lab02 code.zip. Cool. Don't need that anymore. All right, so here's list main, and we had hashset main.c here. It's empty. Let me just grab this entire thing here, list main, and pop it down. and we'll start making some changes. So this should be hash set main hash set.h, I think. Don't need these anymore. That's fine. And I may as well make this the hash sets main application, something like that. This gets me that echoing feature over here. Let's see. Oh, I'm supposed to be making a P2 overview video, which I am. So that's great. Let's see. There's a help message here that is associated with the linked list demo. Let me nix that and instead, in the project 2 overview, since I got so many complaints about needing to type in this set of help messages to be compatible with test cases, I just gave up and gave you something to copy and paste for the help messages here. So that will get me the help part here. Let's see, this is supposed to be quit. Oh yeah, and then let's say I need to change the prompt here to HS. There's no list here. I'm just actually going to comment these out as I need to do something different for the hash tables thing for that. And I don't feel like dealing with it right now. But a lot of this stuff then is going to sort of play out nicely. Instead of exit, it's quit. So I'll just make changes there. And a lot of these commands are different, and I don't feel necessarily like I don't feel like dealing with any of the rest of this stuff right now. So I'm just gonna bop back down, maybe here, comment out this entire thing. And again, if you don't know how to block comments to sort of deactivate code, then that's not it's a good idea to learn how to do it because it's useful in a situation like that. I'm gonna comment this out as well because it's not a list clear. It's some kind of function that will do things in that. And with that, I think this is a functioning main. We're going to try to build the project. So here's P2 code and see if what GCC thinks of it. So make prob3. There's an echo variable, echo set, but not used. Okay, it's a complaints about this thing. Oh, and I somehow managed to get an E in over here. That's not good. So while one is that's fine there because that's just a syntax error. Unused variable success. I feel like I'm using success. Oh, I wonder if it's like just a contingent error where, yeah, so they return 0. It's okay, so now I got some minor problems here. Return with a value in a function is probably a void function or something like that I screwed up. I'm actually going to do this in Emacs because I don't feel like navigating here. So yeah, it's a void, so I need to return 0 there. And then that might be it. So I'll make my problem 3, and there we go. Good. Okay, cool. So with that, I should have then a hash set main application, which I run, which is great, and at least honors my quit and can do the typical make test prob3 business to run the test cases. I'm compatible there for that part. Now, I'm not going to pass much of anything right now. And that's okay because I can start filling in functionality and work incrementally towards passing these test cases. Now, it's worthwhile to state that all of the test cases for this problem are dealing with runs of main. And so there's no specific tests for, are you doing hash set write data ordered properly? Are you doing hash set init properly? Instead, there's more an integration test rather than unit tests, where there's a combination of manipulation of the data structure along with its execution in main. And this is going to require you to have somewhat more sophisticated debugging skills and coding skills because anything you build for functions over here, you can't directly test it until you implement the equivalent functionality over in the main function to say, I need to call hash set init over here, but I don't even know if that works yet until I actually start adding things into it. And I don't know if that works right unless I can actually print some things out. So several functions in here then that are tied to the activities that need to happen in main. This is not the easiest sort of structure, and you're more than welcome to write test cases for all these functions yourself, but in the 10 plus years that I've been teaching, no one's ever written their own test cases for this kind of stuff. They instead use the stuff that I got and then complain that it's hard to debug. But that's your deal now. This is your application. Learn how to run it. Learn how to run it in GDB if you like, so you can set breakpoints to these functions and step through it. But the high-level tests that are provided there exercise most of the functionality in the application, and so are more centered on what a user experience would be like for it. So take that into account as you start your development, that it may take a little bit longer because you have to figure out debugging strategies on your own to get that stuff. And generally, folks often think unit tests are, oh, I test this function and I test this function, I test this function. But that's not a good understanding of what unit testing actually is. A unit is oftentimes a data structure, like here is a hash set. And if you're going to respect the boundaries of that hash set, the abstraction boundaries to say, I don't look at the internals of it, then there's no way to test it without invoking at least a couple functions, add something to it, and then ask, is that thing contained in it or not? So there's no individual test that you could write for hash set add without breaking open the abstraction barriers for it. Rather, a unit test would say, add this and then check if it's contained or not. And so those two functions have to work correctly. And if there's a bug, it could be in either of them. Bear that in mind then as you're working through this thing. Okay, I think that will do it for my overview. The usual criteria apply, that each of the problems has some manual inspection criteria, some test cases associated with it, the exception being Puzzlebox. Sorry, stuffy nose. The Puzzlebox, which is all completely automatically graded. So whatever you get in terms of your input.txt file, that's your score for this. There's no manual inspection for it. And as you wrap up, type the make zip and take that and upload it. Same late policies apply as for the first project. Can submit up to 2 days late at a cost of 1 engagement point per day late. Happy hacking all. This is a fun project. So it touches on a number of different things, and just be cognizant of that first problem. Code things as short and sweet as possible to make your future self happy when you have to recode it in assembly. That'll for me. I'll see you in lecture tomorrow. Cheers.